Hello, everyone. Welcome back. So, today, what we're going to be talking about is actually an overview of the things that we've already talked about in this course. But the thing is, with all of these types of reactions that we've learned, there's a lot of them. All right. And I've actually listed them all out here. There will be a nice list on Canvas that you'll be able to actually look through that is a little bit nicer written out than this. But you can see throughout this semester thus far, we've learned a lot of different reactions. Everything past this line that I'm going to draw right here was all things that we learned after exam two. So, we've learned in the past couple of weeks oxidations, reductions, nucleophilic acyl substitution, a bunch of alkene additions, a bunch of alkyne additions, alkyl nucleophile reactions, and keto-enol tautomerization. What this ends up looking like is 35 total unique reactions. And the thing about these reactions is the first question you may say to yourself is, how do I sort through all of these in my brain? Because it's true that there's a lot of material here that is a little difficult to parse through. And so the entire point of this lecture is to give you a framework for thinking about how to parse through these reactions in your head and the ways to really study for the upcoming final, no matter what type of final you're given. Okay, and there's really three different ways that you can go about figuring everything out. And the first one that we'll talk about here is using basic concepts. Right? And so if we think about using basic concepts, what do I mean by that? Well, I mean, essentially, we're going to be taking all of the stuff that we learned prior to exam one and throwing them into the ringer to think about what's actually going to happen. Because the most basic thing that we see in organic chemistry is that we have some nucleophile that then comes in contact with some electrophile, and those together form a product. Right. And so essentially, if you're able to take this information and work with it like this, you're actually going to end up being pretty well off in terms of being able to figure out organic reactions. Because in order to just use these basic concepts, all you have to do is be able to identify a nucleophile and an electrophile. Right? If you can do that, then you can go forward and you can draw a mechanism, and essentially you can keep drawing until you reach something stable, right? And so whenever you think about using these basic concepts, the one important part about it though is that you really need to understand the basic concepts well. If you don't understand the basic concepts, this is going to be nearly impossible for you to do. All right. But that being said, the real benefit of this technique is that it allows for understanding of mechanisms you've never seen. And why this is important is because sometimes there will be reactions that you haven't seen before. So let's just do an example and think through using this technique in order to really identify a reaction that we have never seen before. And that reaction is going to be what happens if we toss in an alcohol with PCl5. Right? What do we think is going to happen here? Well, first we need to identify what is our nucleophile and what is our electrophile. Best way to do this is just draw both of these out, right? We already have the alcohol drawn out, but what does PCl5 look like? Well, PCl5 would be a phosphorus with five chlorines sitting around it. And we can remember that phosphorus, of course, is happy to have an expanded octet, so it's cool with these five bonds. Now then, thinking about this structure here and thinking about exactly what's going on in the molecule, we would say that all of these chlorines are pulling dipoles away from the phosphorus, right? And so that immediately tells us that this phosphorus has a very large partial positive charge. The other thing that we see with these chlorines is that chloride is a good leaving group. right? So if we have a good leaving group and a major partial positive charge due to dipoles, really there's only one conclusion this leads us to. We would say that this here is an electrophile. And this shouldn't be too much of a surprise because if we think about alcohols in general, these are usually weak nucleophiles, right? Because that oxygen has some lone pairs that it's happy to give away. So we've identified a nucleophile and an electrophile. Now we got to do the second thing, which is draw a mechanism until we reach something stable. So what is that going to look like? Well, the general principle of nucleophiles and electrophiles is that when they come in contact with each other, the nucleophile attacks the electrophile. And in this case, we know the electrophile is the phosphorus. So that means our oxygen is going to come in and give electrons to the phosphorus. But with that, we're also very well aware that we can't give a bond to the phosphorus without kicking one out. And that's why that good leaving group chlorine is important, right? Because we can boot that out and now we've ended up forming a bond between the oxygen and the phosphorus. Now then, this bond between the oxygen and the phosphorus is relatively strong, right? If we look at BDEs, we'd be able to figure that out. But this compound is not stable, right? Because it has a positive charge on that oxygen. And what we know from acid-base chemistry is we can say that this positive charge wants to be neutral, right? Oxygen almost never wants a positive charge. And that tells us that this proton right here is very acidic, right? It looks like a strong acid. So what's going to happen is essentially more of the alcohol that's hanging out in solution can act as a weak base to come around, grab that proton, and give the electrons back to that oxygen. At this point, we have something that now looks a little bit like this. We have to ask ourselves, does this look stable? And the answer is kinda, but not really, right? Because the one thing that we do have floating around in solution is chloride, right? And maybe this chloride can do something special. Well, looking at what we have here, that phosphorus is still very electrophilic, right? So we would say that overall this is still an electrophile. But the thing is, it's kind of changed in terms of what is electrophilic. Because one thing that we do know after looking into some bond association energies is that oxygen phosphorus double bonds are even more stable than oxygen phosphorus single bonds. So, with that being said, if our chloride comes in, does a backside attack on this carbon, kicks out the oxygen. We can form a double bond to the phosphorus, which is good, and then we can kick out another good leaving group chloride. Now then, once we've done this, we have essentially created a situation where we now have this alkyl chloride, which we know is an electrophile, right? And we've also created this phosphorus oxygen double bond with some chlorines hanging off of it. All right. If you look at this structure, you can say that this is also an electrophile, right? It still has those good leaving groups, and it still has the phosphorus with a large partial positive charge. The only other thing we have in solution at this point that matters is chloride. And we know that this is a nucleophile. But here's the thing. Nothing changes if it's added to anything, right? And so at this point, we can say that the p-double bond O is very stable, and so this is the lowest possible energy products. Okay? So this would be an example of using this exact method. And so, if we're thinking about this method, we can list some pros and cons of it, right? The pros of just using this method as your only study technique is that it allows you to understand the outcome of any reaction, right? Which is a very good thing because that's going to make mechanisms easier for you. But there is one important thing that it lacks, and that is, in terms of cons, it doesn't give you a roadmap for reagents or synthesis. Right? And the important one here is synthesis. Because essentially what we're going to be leaning into here at the end of the semester is thinking about how we can use all of the reactions we've learned to create things um, from whatever functional group we want. So, not having any good way for us to think about going from one functional group to another makes this method a little difficult. That's where method number two comes in. And this is what we'll call functional group conversions. Essentially, looking at this, what you're going to have to ask yourself is how can I make functional group A convert into functional group B? All right. And whenever you think about this idea, you may think to yourself, well, what exactly are we asking about? And I'm going to give you a little bit of an example here just by looking at a functional group that's actually used for a lot of different reactions. So let's think about alcohols, right? If you have an alcohol, and say you were going to take this and do some reactions on it to make something that you wanted. What is that something going to be? Well, it depends on what you're looking for. Let's say you wanted to make an ether. All right, you want to take an alcohol, make it into an ether. How would you do that? Well, you'd use the alcohol as a nucleophile, and you would do something like an SN1 or SN2, and that will make you an ether, right? Knowing this is good. The other good thing is, all right, let's say we wanted to make an epoxide. Well, making an epoxide is relatively simple from an alcohol. All you gotta do is an intramolecular SN2, in which the alcohol is the nucleophile. We can also go other directions. Say you wanted to make some carbonyls, right? Any carbonyl that you want to, you can do so through doing oxidation reactions, right? If you wanted to be more specific, one thing that you can't oxidize up to from an alcohol would be something like an ester, right? But you can make esters from alcohols. You just have to use the alcohol in a nucleophilic acyl substitution. And then let's say that you wanted to take this and make it into something like an alkene, right? You could do this as well. You could do that through something like an E1, because you can either use the alcohol as the base, or if you really want to get specific and think about going straight from an alcohol to an alkene, you can do an acid catalyzed E1 where you use H2SO4 to get the alcohol to leave, and then you do the elimination. The good thing about having a roadmap like this is it also shows what happens in the reverse direction, right? Let's say that you have a carbonyl that you want to make into an alcohol. You could do so by reduction, right? Same thing with esters. If you want to take an ester back to an alcohol, you would also do a nucleophilic acyl substitution. Epoxides back, this is going to be something like an epoxide ring opening, something like an ether back to an alcohol. You're looking at an ether cleavage. And then something like an alkene back to an alcohol, you have a lot of options, right? Because all the reactions of hydration, which include oxymercuration and hydroboration, fall under that umbrella. So essentially, when you're thinking about these reactions, they all relate between functional groups. And that's the benefit of them, is if you're able to then understand what functional groups come from what reactions, you can find roadmaps to make whatever you want. All right, with that being said, this entire idea I'm going to post on Canvas, but I'm going to give the entire functional group reactivity web. All right. So keep in mind that the actual web here is going to be posted on Canvas. And being able to understand this is really important. The one thing I will say about this statement right here is try this on your own. Don't immediately go out and just look straight at the web. Because essentially, if you try it on your own, you're going to start to see how these reactions actually interconvert with each other. So, thinking about this in terms of pros and cons, the pros of this approach is that it gives a roadmap for making what you want from what you have. All right. So, for example, let's say you want an ether, but you have a carbonyl. Well, how do you get there? Based on our map, we would say we're going to take the direction of first we do a reduction, right? Because that's going to take our carbonyl to the alcohol, and then we follow that up with an SN1 or SN2 to get to our ether. Right? So this map kind of gives you a roadmap on saying, oh, if I want to get to an alcohol, I just have to reduce it, and then to the ether, I can do an SN1 or SN2. And as long as you can guide yourself through these roads, these pathways, you're going to be able to find any functional group from any functional group you currently have. So just to reiterate that down here, you can take your carbonyl, you can reduce it to get the alcohol, and then you can do SN1 or SN2 to get to the ether. Okay? The other thing that this does that's good is it helps you think of reagents, right? Because every reaction has specific reagents. So it makes you think whenever you look at this roadmap and you see the word reduction. What is reduction? Well, it's using a reducing agent. The reducing agents that we know are, well, a reduction can be done through sodium borohydride or lithium aluminum hydride, right? So knowing those helps us do these different reactions. That being said, there's one very important con that comes along with this. This can be memorized, which doesn't sound bad at first, but that lacks critical information for each reaction, right? A good example of this would be, say we are asked to go from this carbonyl to this alcohol here. Well, we would say that this is a reduction, right? We're going from a carbonyl to an alcohol, and based on what we drew in our roadmap up here, reduction, that's how you do it, right? So it must just be the case that if we add in lithium aluminum hydride, we'll end up getting this alcohol. But the one thing that this doesn't account for is the fact that right here, there is a new carbon-carbon bond. And one type of reduction reaction is using a Grignard. Right? Grignards are able to do this as well. So what we would actually use here would be the methyl magnesium bromide in THF, followed by HCl and water. Right? So in both cases, this is still a carbonyl, in this case a ketone, to an alcohol, but a normal reductant does not work. Right? If we need that CC bond, it must be a Grignard. So you can use these roadmaps to help really figure out exactly where you're going with everything. But the more important thing is don't use it as a crutch to just assume everything makes sense, right? You still need to understand the intricacies of each reaction. So with that being said, that's where the third approach comes in. For approach number three, we can combine number one and number two. And you can think about what this would be like. Let's think about it in terms of we know by our roadmap an alcohol via SN1 or SN2 will get us to an ether. The question becomes, though, how does this reaction actually work? Right? The first thing we know is that when we see the word alcohol in this case, it's a nucleophile, which means it needs an electrophilic reagent, right? And so we know based on our reaction understanding, which is what we thought about in number one, and based on our roadmap, which is what we think about in number two, we're learning some things about the reaction that we need to do. So in this case, we know we need to provide an electrophile to get this reaction to run. So let's say that we wanted to take this alcohol drawn here in blue, and we want to generate this ether, which I have kept the same chain from the alcohol in blue, and then I've made the other side red. Well, if we think about this, we know that the red piece here, this must come from an electrophile. So this should be easy, right? We throw in an electrophile, and we know for SN1 or SN2, we need a good leaving group on that electrophile. So iodine's a good one. There we go. Great leaving group, right? This is a good leaving group for an electrophile. Now then, we would say that if we were just using number two, that this is great. Everything's done. But once again, we need to use that knowledge from number one and the intricacies of each reaction to really understand what's going on. Because if we think about this alcohol over here, this is a weak nucleophile. Now, that's not too much of a problem until you recognize this is a primary carbon with a leaving group on it. And we know from our mechanistic understanding that this can't do SN1 because it's a primary. So we need to have a strong nucleophile. All right. So if we have a weak nucleophile and we want to make it strong, remember the entire idea of a strong nucleophile is that it's negatively charged. So now we ask ourselves, how do we make this negatively charged? Well, we use a base, right? Essentially, this base is used to make the nucleophile strong. And so now that we have a strong nucleophile, we can do SN2, which we need to do because it's on a primary carbon, and we started out with a weak nucleophile. So in reality, now the entire mechanism of this reaction that we have drawn is that first, hydride acts as our base, grabs the proton from the alcohol, deprotonating it and making it into an alkoxide, which is now a strong nucleophile, which is good for SN2. And now this can come in and do a nucleophilic displacement, a substitution of that iodide, right, which was our primary leaving group. And then that ends up giving us our final ether. Now, if this was just one where we had to make a tertiary ether on the other side, it'd be a little easier, right? Because we could do SN1, we wouldn't have to make it a strong nucleophile. But the thing is, you need to be able to discern that when you're doing these types of reactions. So essentially thinking about approach number three, there's no cons of this approach. Essentially, it allows you to explore all chemical space. and that's going to come really in handy. So this lecture is very short, but the idea is that you're going to take the tools here and you're going to start applying them to actually figuring out how to bring all of these reactions together for synthesis, which is what we're going to be starting soon. And so I'm going to post that roadmap along with every reaction you've learned on Canvas. That way you can start to take all of that and you can learn to understand how the roadmap works. And then from there, you should be able to use that during synthesis to guide your way through and understand exactly why we're doing everything we're doing. So with that being said, I'll see you next time as we start to dive into synthesis and retrosynthetic analysis, and that'll be the way that we end our semester is by going through all the synthesis stuff. So I'll see you next time.